We have discussed several instructions used in SAP 2 in previous lecture. Now we will discuss other instructions used in SAP 2. First of all, we will discuss about call and return instructions. These are related to subroutine. A subroutine is a program stored in the memory for possible use in another program. So subroutine is a small program inside another program. Many microcomputers have subroutines for finding sines, cosines, tangents, logarithms, square root, etc. Call and return, these two instructions are related to subroutine. CALL, call, is the mnemonic for call the subroutine. Every call instruction must include the starting address of the desired subroutine. If a square root subroutine starts at address 5000H and a logarithm subroutine starts at address 6000H, then the execution of call 5000H will jump to the square root subroutine, and execution of call 6000H, this will jump to the logarithm subroutine. RET stands for return. So this is the return instruction. RET, it is used at the end of every subroutine to tell the computer to go back to the original program. Role of return instruction is same as that of halt for a program. When a call is executed, the contents of program counter are automatically saved in the memory locations FFFEH and FFFFH, the last two memory locations. These are last two memory locations, FFFEH and FFFFH. When a call is executed, the contents of the program counter are automatically saved in these last two memory locations. The call address is then loaded into the program counter, so the execution begins with the first instruction in the subroutine. After the subroutine is finished, the return instruction loaded the addresses in memory locations FFFEH and FFFFH into the program counter, so the computer return back to the original program. Figure C shows the working of call and return instructions. This is the figure showing the working of call and return instructions. The call 5000H instruction sends the computer to the subroutine located at 5000H. This is the call 5000H instruction, and this sends computer to the instruction loaded at memory location 5000H, which is the starting instruction of given subroutine. After this subroutine has been completed, the return instruction sends the computer back to the instruction following the call. When subroutine is completed, the starting instruction of subroutine is at memory location 5000H. When this subroutine is completed, then this return instruction RET, this bring the computer back to the instruction immediately followed by call instruction. Call is unconditional. Once a call instruction has been fetched, the computer will jump to the starting address of the subroutine. Logical instructions. SAP2 logical instructions are following: CMA, ANA, ORA, XRA. These are related to complementary. CM, AN for AND operation, OR for OR operation, and XR for XOR operation. And A is written in front of all these instructions. This A is for accumulator. CMA, CM is for complementary and A is for accumulator. CMA stands for complement the accumulator. The execution of CMA instruction invert each bit in the accumulator, which produce the ones complement. So execution of CMA instruction will produce ones complement. Each bit is complemented or inverted. Next instruction is ANA. ANA means to AND the accumulator contents with the designated register. The result is stored in the accumulator. For example, ANA B. This instruction means to AND the content of accumulator and content of B register. If content of A register is A equal to 11001100 and content of B register is 11110001, then the execution of ANA B results in A equal to 11000000. The ending is bitwise as shown in this figure. There are 8 bits in the word stored in accumulator A, and there are 8 bits in the word stored in B register. A7 is ended with B7, A6 is ended with B6, and so on. So this AND operation is bitwise. Here A7 is 0 and B7 is 1. So when A7 is ANDed with B7, 0 and 1 will give 0. So result is 0. And similarly other bits are ANDed and result is stored in the accumulator, and accumulator content now becomes A equal to 11000000. Two ANA instructions are available in SAP 2 because with accumulator A we have two more registers, B and C registers. So two ANA instructions are available, that are ANA B and ANA C. We can AND the accumulator content to the content of B register, and we can AND accumulator content with content of C register. Next logical instruction is ORA. ORA is mnemonic for OR the accumulator with the designated register. The result is stored in the accumulator. For example, ORAB, this instruction means OR the content of accumulator with the content of B register. If A is 11001100 and B is 11110001, then the execution of ORAB will result A equal to 11111101. Here the OR operation is also performed bitwise. A7 is 0 and B7 is 1, and OR operation will give 1. So resultant of A7 or B7 will give 1, and it is stored in the accumulator. So accumulator content becomes 11111101. Next logical instruction is XRA. XRA means XOR the accumulator with the designated register. The result is stored in the accumulator. For example, XRAB means XOR the content of A register, that is accumulator, with the content of B register. If A is 11001100 and B is 11110001, then execution of XRAB results A equal to 00111101. Now XOR, exclusive OR operation, is performed bitwise. For example, if here A7 is 0 and B7 is 1, then XOR operation will produce 1, and so on. Some other logical instructions are ANI, ORI, and XRI. These are related to AND, OR, and exclusive OR operations, and I is for immediate. ANI means AND immediate. It tells the computer to AND the accumulator contents with the byte that immediately follows operation code. For example, if A is 01011110 the execution of ANI C7H will end the accumulator content, that is 01011110, with this byte, that is C7H. H is for hexadecimal. C7 in hexadecimal number system is equivalent to this byte, 8 bits. C is equivalent to these 4 bits 1100 and 7 is equivalent to these 4 bits 0111. So we have to write a byte in front of ANI instruction. ANI C7H will end the accumulator content with this byte, that is equivalent to C7, and this will produce new accumulator content A equal to 01000110. Similarly, other logical instruction is ORI. ORI means OR immediate. It tells the computer to OR the accumulator contents with the byte that immediately follows the operation code. For example, if A equal to 01011110, the execution of ORI C7H will OR these 2 bytes. One is accumulator content A 01011110, and other is this byte which is written in front of ORI, that is C7H. C7H is equivalent to this byte 11000111, and OR operation will produce new accumulator content, that is A equal to 11011111. Other logical instruction is XRI. XRI means XOR immediate. It tells the computer to XOR the accumulator content with the byte that immediately follows the operation code. For example, if accumulator content A is A equal to 01011110, the execution of XRI C7H, correct this, it is not XORI, it is XRI C7H. This will XOR these 2 bytes. One is accumulator content 01011110, and other is this byte C7H, which is equivalent to 11000111, and XOR operation bitwise will produce new accumulator word, that is A equal to 10011001. Other instructions. First is NOP. NOP stands for no operation. During the execution of NOP, all T states do nothing, and no register change occur during a NOP. This instruction is used to waste time. 4 T states are used to fetch and execute NOP instruction. By repeating a NOP a number of times, we can delay the data processing, which is useful in timing operations. Other instruction is HLT. HLT stands for halt. It ends the data processing. There are input and output instructions. IN for input instruction, OUT for output instructions. In is the mnemonic for input. It tells the computer to transfer data from the designated input port to the accumulator. Now in SAP 2 we have two input ports, input port 1 and input port 2. So this input instruction tells the computer to transfer data from designated input port to accumulator. Since there are two input ports, we have to designate which one is being used. The format for an input operation is in byte. For example, in 0 to H means to transfer the data from input port 2 to the accumulator. Similarly, we can have other instruction IN01H, which will transfer data from input port 1 to the accumulator. Similarly, we have out instruction. Out is mnemonic for output. It tells the computer to transfer data from the output port from the accumulator to the designated output port. So output instruction will transfer data from accumulator to output ports. Since we have two output ports, output port 3 and output port 4. Since there are two output ports, we have to designate which one is being used. The format for an output operation is OUT byte. For example, OUT 03H means to transfer data from accumulator to output port 3. Similarly, we can have instruction out 04H, which will transfer data from accumulator to output port 4. Two other instructions are RAL and RAR. Rotate accumulator left and rotate accumulator right. RAL is mnemonic for rotate the accumulator left. R is for rotate, A is for accumulator and L is for left. Rotate accumulator left. This instruction will shift all bits to the left and move the most significant bit into the least significant bit positions as shown in figure A. All bits are shifted to left, and in the last, this most significant bit MSB is shifted at the position of LSB, least significant bit. So RAL instructions shift all bits to left and the most significant bit goes to the position of least significant bit. If the content of accumulator are A equal to 10110100, then execution of RAL, rotate accumulator left, this will shift all the bits towards left. So shift all the bits toward left, and the MSB, most significant bit, that is 1, this will goes to the least significant bit position LSB, and all bits are shifted towards left, and new accumulator content will become now 01101001. All bits moved left and the MSB went to the LSB position. RAR is mnemonic for rotate the accumulator right. This instruction will shift all bits to the right and move the LSB into MSB position as shown in this figure. Rotate accumulator right, RAR, all bits are shifted towards right. When all bits are shifting towards right, then this least significant bit will goes to the position of most significant bit MSB. If accumulator content is 10110100 and we shift all the bits towards right, and LSB, which is 0, it goes to MSB position. New accumulator content now becomes 0101 1010. This is due to execution of RAR, rotate accumulator right.